In the sixth example, they throw in a little bit of vocabulary and some ideas of what a reduction identity is. Sum and difference identities can be used to rewrite trig expressions in which one of the angles is a multiple of 90 or pi halves. And this is I guess the important part of it all. If it's a multiple of 90 or pi halves, the resultant identity is called a reduction identity. So they're given a certain name, a reduction identity, because they're multiples of 90 or pi halves, and they say it typically reduces the complexity of the expression. So we're just asked to identify, using our sum and difference identities, these different reduction identities. So what we do is we're going to run through the cosine of the difference. We're going to prove that it's equal to the cosine of theta. So the cosine of the first angle times the cosine of the second angle. Then we go plus sine of the first angle, sine of the second angle, and we're hoping that we can get that to reduce to cosine of theta. A cosine of 360, again, we're looking at an angle that goes all the way around, parks itself right on the x-axis, which is the order pair 1, 0. So the cosine of 360 is 1 times the cosine of, that was a theta, so cosine of theta, plus the sine of 360, that is 0, so 0 times sine of theta. And really what we're left with is a cosine of theta plus 0, or just the cosine of theta, and we've already proven this reduction identity. Okay, pretty straightforward and simple. Just got to work with some quadrantial angles. Okay, second example. This time it's the sine of a sum. So we take the sine of the first angle, which is pi halves. We take it times the cosine of the second angle, which is x. We put plus cosine of the first angle, which is pi halves, times the sine of the second angle, which is x. We want to prove that it's equal to just the cosine of x. Pi halves, we just got done looking at it, but I can do another diagram on it, reference. It's pi halves is a 90-degree angle, which means we're parked here on the y-axis, which is 0, 1. So our cosines are 0 and our sines are 1. So sine of pi halves is 1. Take it times the cosine of x. Plus the cosine of pi halves is 0, so you take 0 times sine of x equals, we want to prove it's the cosine of x. So it's really the cosine of x plus 0 equals the cosine of x, which means the cosine of x is equal to the cosine of x. But you can see there's not a lot of stuff that goes into these, but what are some important things that you put in? Make sure that you're putting in the 1 and the 0. Don't just say, well, I know what it is, so just put it in there. And I think you should also put this in here. They're not real involved in detail without that. Otherwise, if you don't put those details in there, there's not much that you're going to show, and you're just going to say, oh, well, it's obvious it's cosine of x. But it's the details that you show in your proof that helps the reader follow through and understand what you're doing. So don't get too short on those. We want to make sure that we're clear in spelling out how we're verifying those identities.